Good morning, guys. Today we're going to look at complex numbers. What is a complex number? We'll talk about that in a second. Let's first start by looking at this equation we've got over here. X squared plus 18 equals 2. We want to solve this equation. Well, we'll just do that by isolating the variable. So I'm going to move my 18 to the other side by subtraction. X squared equals negative 16. We get rid of the square by taking the square root of both sides. X is equal to plus or minus. And then at this point, we have to answer the question. What number squared equals negative 16? What number times itself equals negative 16? Well, on first glance, most people say negative 4. Negative 4 times negative 4 equals positive 16. Positive 4 times positive 4 equals positive 16. To get a product of two numbers to equal a negative, one of those values has to be negative. Negative times a positive is the only way we can get a negative value. So if we want a square root where it's the exact same number being multiplied by itself, that's not possible, because if one's got to be positive and one's got to be negative, then it's not the same number. And for years you would just say there's no real solution, or you would just stop working. But no real solution is what you would say, and there's a lot of truth in that. There is no real solution. But what we do have is an imaginary solution. Many, many years ago, Leonard Euler said, what if we didn't just say that there's no answer, we can't go, this isn't possible? What if we just said, okay, there's a negative in there, let's acknowledge that there's a negative in there, and let's keep going and see where the math takes us, where the numbers take us from then on. So he came up with this idea called the imaginary unit. And the imaginary unit, which we call I, that's just a little italicized I, or cursive I is what I'll always write. And that I is equal to the square root of negative 1. So he said, instead of stopping and saying, well, I can't go any further, this is as far as I can go, I could look at it as any other radical. 16, or negative 16, is negative 1 times 16. Well, we know the square root of 16. That's no problem. That's 4. It was the square root of that negative 1 that was always the issue. And he came up and said, let's just define that as I. Let's just define the square root of negative 1 as I, so that I can say x is equal to plus or minus 4i. Well, that may seem trivial. You could have left it 4 times the square root of negative 1. But that I becomes very important, because now we don't have to stop right here. We can take that answer and use it in the next step of our equation, or whatever the problem is we're trying to work out. And there are a lot of important things that have come because of that. Being able to use that I shows up quite a bit in aerodynamics. It shows up in electrical, or the flow of electricity, electrical current, things of that nature. So the fact that we didn't stop at square root of a negative and just say this isn't possible, and we went with this defining the square root of negative 1 as this I, this imaginary unit, we were able to keep going and do a lot of very important mathematics. So that's what we're going to focus on today. That's where complex numbers come in, and that's starting to talk about not just real numbers, numbers I can put on a number line, but also imaginary numbers. Numbers that have this imaginary unit with it, this square root of negative 1. So today we're going to look at just kind of the arithmetic involved with complex numbers and imaginary numbers in general. So we just established that the square root of, or that I is equal to the square root of negative 1. Well, what do you think the square root of I squared would be? Well, let's look at it. If I take square root of negative 1 and I square it, what happens when you square a square root? And we'll look later on about how a square root is actually an exponent. But when you square a square root, the square root dumps. So we're left with negative 1. This is where this stuff starts to have some important value to it. So I squared is actually equal to negative 1. It's the only time you can square and get a negative, because any other times you multiply a number by itself, it would come out to be positive. Well, let's look at what I cubed would be? Well, I cubed we know is just I to the first times I to the second, right? I to the first times I to the second. Well, if I to the first is just I, and I to the second, so I to the first is just I to the second is equal to, well, we already said -1, then I to the third would be equal to -I. Well, what do you think I to the fourth would be then? If we thought of it as I squared times I squared was -1, I squared is -1, and -1 times -1 is +1. I to the fifth, what do you think? Well, it's I to the fourth times I to the first. I to the fourth, we just said was +1. I to the first is I, so that's I. So what we see is we get this pattern. I to the first is I to the second is -1, I to the third is I to the fourth is 1, and then we start to repeat. I to the fifth becomes 1 again. So if we were to do something like I to the 74th, well, we know every time we get 4 of them, that's 1, and then the cycle repeats. Well, 74 is, if we did it divided by 4, 74 divided by 4 is going to give us, well, let's see, that's 4, subtract, you get your 3, bring down your 4, going to that, 18, that's your 32, 2 left over. So it goes through the cycle 18 times. Cycle of 4, cycle of 4, cycle of 4, cycle of 4, cycle of 4. Goes through the cycle 18 times, and then, so it's I to the fourth 18 times, and then we had 2 more i's left over, with an I squared left over. Well, it doesn't matter how many times it goes through the cycle, I to the fourth is always going to be 1. So what we get is 1 times I squared, which is -1. So I to the 74th power equals -1. So we can evaluate I to any degree, we can evaluate I to any degree, or any whole number degree, and be able to work out what it actually is in this, out of this cycle of 4. Give me a couple of seconds and I'll get some examples up, and we'll look at how we just combine different types of complex numbers, or numbers that have I in them. Before we start doing some work with complex numbers, just let me define what a complex number is for you. Complex number is any number of the form a plus bi, where a and b are real numbers. I is obviously the imaginary unit. Now we can see if b is equal to 0, we have 0 times our imaginary unit leaves us only the real numbers. So a plus bi is real at that point. If b is not equal to 0, then a plus bi is an imaginary number. So every single number is complex. This a gives us the real component. The bi gives us the imaginary component. Real component and imaginary component. So what we can see is I could write every number as a complex number. The number 4 is complex because I could write it as 4 real plus 0 imaginary parts. 4 plus 0i. The number -2i, that is also complex because I could write it as 0 real parts and -2 imaginary parts. And then you obviously have things like 4 minus 2i, which has real and imaginary components, but because it has the imaginary at all, that means it is just imaginary. You can have both components, but if it has the I anywhere in there that's attached to something other than 0, then it is going to be imaginary. So this is when we say write a number in complex form, we need to identify what the real and imaginary components are. That's going to come in handy because we're going to start graphing these in a little while. But first, let's look at just adding, subtracting, and multiplying and dividing these complex numbers. Okay, let's do a few operations where we simplify expressions where I is involved. So let's look at number 1 right here. We want to simplify the square root of -25. Well, we know the square root of the 25 is 5, and the square root of negative is I. So if we just take the second to write it out, -1 times 25. Answer the question, what's square root of 25? 5. What's the square root of negative 1i? So 5i is our answer. If I had something like square root of negative 12, 12 is not a perfect square. So when I rewrite this as perfect square factors, it's negative 1 times 4 times 3. 4 is the perfect square, it goes into 12. And then I just answer the question. What's the square root of negative 1? I. What's the square root of 4? 2. What's the square root of 3? I don't know. So I leave it. 2i came out. Square root of 3 was left in. Let's say we have something like number 3 here. I just stands for the square root of negative 1. So adding and subtracting i's is just adding and subtracting square roots of negative 1. We're just counting how many we have. So if I look at this, just put the things that are like together. Combine your real components, combine your imaginary components. So 4 minus 7, negative 3 real components, 2i minus 4i. So if I have 4 i's and I take away 2 i's, I'm left with 2 i's. So that's minus 2 i's. 2i minus 4i is negative 2i. That's how you could do that. Just combine the parts that are like, just like you would any other variable. Number 4, we're going to multiply. Well, how do you think we multiply these complex numbers? Distribute, just like you would any other multiplication. 3 times 4 is 12, minus 15i, plus 8i, minus 10i squared. Clean it up. 12 minus 7i, 15i and 8i, sorry, negative 15i and 8i is negative 7i. Negative 10, but that I squared, we remember I squared equals negative 1. So 10 times negative 1 is 12 plus 7i plus 10. 12 and 10 is 22 plus 7i. Sorry, minus 7i. 22 minus 7i. So the product, the sum of complex numbers will be complex numbers. 5 minus I quantity squared. Again, remember you can't distribute exponents across addition or subtraction. So I have to actually make this into a multiplication problem. 5 minus I times 5 minus I. Now we treat it just like we do number 4. Distribute it. 25 minus 5i minus 5i plus I squared. So 25 minus 10i, we know I squared is negative 1. 25 and negative 1 gives us 24 minus 10i. So that's how you simplify radicals that have negatives involved. That's how you add or subtract complex numbers, multiply complex numbers. Let's say that I had a division problem involving complex numbers. So we'll go with let's just go 2 plus I over 3 minus 2i. 2 plus I over 3 minus 2i. Now to be able to work this out, to get a single complex number, some real component plus or minus some imaginary component, I've got to use what I remember about radicals. I is just square root of negative 1. We can't leave radicals in the denominator, so we have to remember we multiply. We have to create that perfect square scenario in the denominator so square root cancels out. Remember, if you have a plus or a minus in the denominator, take a step to the side real quick right here. So say I had 3 over 1 plus square root of 2. To get rid of that square root of 2, I had to multiply by 1 minus square root of 2. We called that the conjugate. And if you'll remember why, because when you distribute all this, 1 times 1 is 1, plus square root of 2, minus square root of 2, minus square root of 4. The square roots cancel, and the 2 and 2 get multiplied to give us 1 minus 2, which in this case would be negative 1, and you just do your negative from there. So negative 3 plus 3 square root of 2. So that's how you rationalize when you have a radical and denominator that's part of a binomial. Multiply by its conjugate. Well, we're going to do the exact same thing here. And we're going to multiply by what we call the complex conjugate. Complex meaning it has an I in it. Conjugate meaning opposite the square root. So complex conjugate just implies opposite the I. So we're going to rationalize like we've done before, but instead of multiplying by just the 2i, because that would just shift it over to the other term when you distribute, we're going to multiply by opposite the I. 3 plus 2i, numerator and denominator. So when I go through it, now it just becomes a multiplication problem. Put your parentheses in there to help you remember to distribute. 2 times 3 is 6, plus 4i, plus 3i, plus 2i squared. Denominator, 9, minus 6i, plus 6i, minus 4i squared. So we're just distributing. We'll go through and combine our like terms. Let's clean it up. So 6 is 6. 4i and 3i is 7i. 2i squared is going to be 2 times negative 1. 9. Negative 6i, positive 6i cancel, so our i's are gone because we know I squared is negative 1. That's why we multiply it by complex conjugate, because it will cancel out the I. So if we finish this up, 6 and 2, negative 1 is negative 2 is 4, plus 7i, over 9, negative and negative makes positive, so that's 13. So we get 4 thirteenths plus 7 thirteenths I. So we have divided two complex numbers to produce a single complex number. So we can add them, we can subtract them, we can multiply them, we can divide them. We can simplify a radical that has a negative in there so that it has an I. We can raise an I to any power we want and be able to simplify that down. So we can do a lot of stuff with I, but it's really just following the same rules of multiplication addition that you use for any variable expression. Only thing that changes is if I has an exponent on it that's not 1, we just have to go through our cycle of 4 to figure out what it actually would be. In terms of either I or negative 1 or negative I or positive 1. Give me a second, I'll show you how we're going to graph complex numbers and identify their absolute values. Okay, let's look at how to graph a complex number. We know how to graph a real number, we just put it on the number line. Well, the complex number actually has two components to it, the real component and the imaginary component. So we need a plane instead of a line. So what we do is we take our real number line and we extend a vertical axis, and we call that the imaginary axis. So we're going to graph the real component based on where it matches up on the real number line, the imaginary component based on where it matches up on the imaginary number line, the imaginary axis. So let's say we have negative 4 plus 2i. So I go to negative 4 because this is my real component. Negative 4 is the real, 2 is the imaginary. So I go to negative 4 on the real axis. I go to positive 2 on the imaginary axis. And we just find and that is the point, or the number, negative 4 plus 2i. So if we took something like 2 plus I, 2 is my real, that'd be 1 for my imaginary, 2 on the real, 1 on the imaginary, 2 plus I. So it ends up graphing just like an ordered pair. Negative 4 comma 2, negative 4 comma 2, 2 comma 1, 2 comma 1. So how do you think we would graph negative 3i? Well, we see 0 real part, so I'm not going to move on my real axis. And we see negative 3 imaginary parts. So 0 for my real, negative 3 for my imaginary. So we can read it like the order pair, 0, negative 3, where we're working with reals and imaginaries instead of x's and y's. Now let's say that we wanted the absolute value of negative 4 plus 2i. I want the absolute value of negative 4 plus 2i. Well, what does absolute value mean? It doesn't mean take whatever's inside and make it positive. Absolute value means the distance from the origin. So if here's negative 4 plus 2i, I need to find how far it is to the origin. Well, we know how to do that because the origin is 0 plus 0i. It's just 2 points. I'm finding the distance between 2 points. So we remember distance formula between 2 points square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Distance between my x's, distance between my y's, you get the sum of the squares of the hypotenuse of a right triangle is equal to the sum of the squares of the legs. So distance formula we know is just a manipulation of the Pythagorean theorem. Well, it gets even cleaner when we're doing it with these because our x1, y1 is always 0. So the absolute value of an imaginary number is just square root. The distance from that number to the origin is the square root of your x value squared, or our real value in this case. So we'll call that a squared, plus the y value, the height, which in this case is our b squared. So if z is a plus bi, so if we want the absolute value of a complex number, we do square root of a squared plus b squared. So if we go through here, we do square root of negative 4 squared plus 2 squared. Square root of 16 plus 4 is 20. Clean it up. 4 times 5, so 2. Square root of 5. So negative 4 square root of 2 is 2 square root of 5 units away from the origin. So that's how you find the absolute value of a complex number. You're doing distance formula from that point to 0, to 0, 0, which when we clean it up, we end up getting it as square root of the real component squared plus the imaginary component squared. I don't need the I in there. It's not a squared plus bi squared. It's just a squared plus b squared. The I is what told us to move up or down. It doesn't tell us, it doesn't come into any account when we're talking about the actual distance. It was just our direction. Okay, so complex numbers, we know what they are. We know how to graph them, find absolute value, do all kinds of arithmetic with them. So now we've kind of completed the picture on all possible numbers. We have the numbers that we can graph on a number line, the real numbers. We have the numbers that don't fit in there, the imaginary numbers, and all together they make the complex numbers. We will continue working with these throughout the year, throughout the course, and hopefully they'll kind of open up even more possibilities about what you can do in going forward in math. That's complex numbers, and I will see you in class tomorrow, guys.